finding is VTC. It would be good. I like this approach. This is instructive and help you understand an inverter better. So how do we find the VTC, right? You can solve the equation. You can do spikes. But there's one thing called low line approach. So what does it mean? It means that, first of all, what is this? This is IDSN. And this is IDSP, right? Again, D is here, S is here, just by definition, right? So I say IDSN equal to negative IDSP because they're pointing in different direction, but the currents should be the same going up and down, right? The same current go from the VDD to drain to source. So IDSN equal to IDSP. And then, of course, then I would just use the equation, right? This is NMOS. I know it very well. This is PMOS. I can draw the so-called IDVDS curve, right? But can you tell me for NMOS, what is VDS in this figure? VDS is just V out minus 0, which is equal to V out. Right, so in an inverter, the VDS for NMOS is just V out. How about VGS? Can you tell me what is VGS? Based on the quantity in the Vin minus 0 equal to Vin. That's easy. How about for PMOS? What is VDS in PMOS?
VD minus V out.
Okay, so we need to be very careful. VDS means VD minus VS. So what is this again?
V out minus VDD.
Exactly. Yeah. And that's why you get negative value, right? Because V out is always smaller than VDD, right? How about VGS? What is that?
VE minus VDD.
Exactly. Yeah. Looks very weird, but you just need to do this step by step. Okay, so a general picture on how we assign them. So then now I need to transform them. I cannot compare them because I have different XS's, right? So what I'm going to do is start with PMOS. This is the PMOS IDVD, right? If you look at here, do you see that? It's all in the negative. So in the third quadrant, that's what we are putting here, right? So let me repeat one more time. VDS is just equal to V out minus VDD, right? And VGSP equal to V in minus VDD, okay? So the first transformation is this. I want to change IDP to IDN. But I already told you what is IDP. IDP is just equal to negative IDN, correct? So all I need to do just flip the curve. That is one thing. And another thing is that because here I don't write it clearly, VGSP, right? VGSP equal to this one. So it also means that V in equals to VDD plus VGSP, right? So instead of calling VGSP equal to negative 2.5, I can call it is V in equal to, I forgot to tell you, actually, I set the VDD equals 2.5, right? Assume, right? Equals to 2.5 plus VGSP, which is minus 2.5 equals 0, right? And I point to the wrong one because this is a bottom figure. It should be here, right? So indeed, when your VGS is negative 2.5, right? Which is true, right? When your 3dD is negative 2.5, it means that your V in is 0, right? That's why V in minus VDD equal to negative 2.5, right? So you just flip the figure out, just a mirror image. And I continue to do this. Now I transform the VDSP to V out. And just like what we are saying here, right? Actually, it's written here already, but I just duplicated. VDSP equal to V out minus VDD. That's why V out equals to VDD plus VDSP. Okay, so all I need to do is just shift the whole thing to the right by VDD. Okay, then I get this curve. But now you see that the y-axis is ID, the x-axis is V out. Is this okay? So if we get this curve, then we can overlap it with the CMOS, because this is IDN, this is V out, right? So which one is CMOS? This is CMOS. CMOS is like this. Okay. And then PMOS, these are the PMOS. Right? These are PMOS. And then we say that they should have the same current, right? Because both of them are on the same scale. The V out need to be the same. The IDS need to be the same. So the crossover will be the solution. Of the crossover, you also do make sure that they have the same V in also. For example, here, let's take an example. This graph, this blue line, right, is NMOS with V in equal to 1. And then this red line is PMOS with V in equal to 1. And this point, you have the same V out, you also have the same ID. So this is a solution. So I can plot the VTC. Right? I start with V in equal to 0. So when V in equal to 0, which is this point, right? The intercept is this point. Because at this point, this is the PMOS and this is the NMOS. Because it's 0, so it's off, it's turned off, right? And then I intercept at this point. So the V out is here, VDD output. Okay. And then I go to V in equal to 0.5. When V in equal to 0.5, it gives me this curve. For NMOS. And then for PMOS, this is 0.5. So this is the curve. And it intercepts here, right? So I increase the V into 0.5, it dropped a little bit, right? And then I continue to go to 1 volt. I already mentioned earlier. The V out again drop, but not as much, like this. Right? And then if I switch to 1.5, I switch to 1.5, then V in becomes this curve, right? But the PMOS one is this one. This is 1.5. Right? So you see it change quickly. V out jump quickly from high to low. And that is the characteristic of the device, right? And you continue something similar, which I'm not going to repeat. You get this black to black dot. And then you get this VTC. Okay, so this is the low line method. I think this is very instructive because it helps you to understand the region of operation. Let me ask you, for the green one, right? For the green one, what is the region of operation for NMOS at this point? If you look at its curve, is it on, linear, or saturate? Right? Remember, this is when V in equals 0. This is the IDVD for V in equals 0 for NMOS. Is it on or saturate or
It's off. Cut off.
Off, because the VG, right, which is V in, is less than VTH. But how about for PMOS? Look at the curve. Is it on, off, or saturate? PMOS is V in equals 0, right? And it is at this point. First, is it on or off?
It is on and in trial.
In trial. Because it is in this deep region, correct? Very good. So here I call it resistive, right? Which is linear or trial, okay? I just want to use the same terminology as the book in the next slide. Okay, so right, so you can see that how it works. Then gradually, when it comes to here, how about this one? What is NMOS?
Saturation.
Saturation? Because it is on the other side, right? How about for PMOS? We just look at the curve. This is 0.5. This is the curve. So which region is that for PMOS?
Resistive.
Yeah, still linear or resistive. Okay, then you will just keep doing this, right? And there will be a point eventually, both them will be, but not in this figure, so I did not draw it well, right? But there will be a point, maybe here. Both of them are in this straight line part, right? The flat part. Both of them are in the saturation. Right? So you see it go from linear to saturation. And then you're going to swap. You will go to can you guess what will happen to the NMOS when you go to high? Because now that you all fall to this region, right? So NMOS is what?
Trial.
Trial, yeah, trial, yes. Right, and then PMOS continue to be at saturation. But eventually what happened? NMOS is still in the trial region, resistive region, and PMOS becomes, at this point, the PMOS is just a straight line, horizontal line, right? Off. Is this okay? Right? And that is exactly what it happened, say here, right? Let me check if I do the right thing, because I don't have cheat sheet. Right. Saturation, resistive, off, yeah? So that is basically what we say, right? NMOS go from off to saturation and then resistive. PMOS go from resistive to saturation and then off. So this region is saturation, and depends on what you're trying to study. You need to use the right equation. Right? But you see that they are all mostly in saturation in the region we are interested in. So we can use the saturation equation, right? This region is mostly saturation. Although this one may go to resistively gradually, but depends, right? It's still mostly saturation. Okay. So then we get the load 9.